everyone. Thank you for coming. My name is Eric. I'll be presenting for Professor Ali Reza Ramezani from the Northeastern University, working under Silicon Synapse Laboratory. So the topics for today is the mechanism design of a bio-inspired arm ring mechanism for mimicking a bat flapping gait. So the goal of this project is to mimic bat flapping gait, particularly like this bat over here. So it's like bat has a very articulated gait, flapping gait. It has 46 modes involved, like this that creates a very complex flapping gait. Has more than 40 joints on each wing, so it's like it's very unlikely that we can actually mimic all of these modes in entirety. So we resolved to just mimic two modes, primarily the flapping gait and the elbow flexion and extension. The flapping is just the up and down wing movements, like which is the core flapping gait, and we have this elbow flexion and extensions, which has the effect of folding the wing during the upstroke and expanding it during the downstroke. So this creates a very efficient gait where the negative lift is minimized during the upstroke and can achieve a more efficient flight. So it's like there are more than these two modes that's important during the flapping motion of the bat, and we might try to incorporate those other modes in the future work. So I'm going to show you a video of this robot called AeroBat for the wing design that we created. So you can see like this is the render and how the wing motion that we plan it to have. So it's like during upstroke it folds and during downstroke it expands. So trying to mimic some of this bat flapping gait motion that you see over here, which is very articulated. It's very flexible and looks cool. So here's the the initial design we have on this wing mechanism. We have the kinetic sculpture over here, which has rigid and flexible component monolithically fabricated using polyjet 3D printing. We have a lot of gears and transmissions. Like most of these gears are operated using like 4-bar linkages. So you can see like how it's driven towards the driving mechanism over there. So it's like this is the kind of motion that we want. All of this is driven by just a single motor, and as you can see over here, like all that flexible joints is working over there to replace rigid hinges. So we have this kind of transmission. It's like I plan to use some PLDCs, and we're trying to finalize this design like eventually and try to do some untethered flight at some point. Alright. So this is the arm ring transmission mechanism that we have that actuates creates the flapping motion. So it's basically a series of gear, cranks, and 4-bar mechanism. In this case, like this actuates the shoulder joints to have a plunging up and down movement. Then we have another 4-bar mechanism that's the movement in relation to this elbow joint creates this elbow flexion and expansion, which basically folds and expands the wing. All of this is actuated by single motorized gear over here, and these two mechanisms basically creates the two modes for flapping and elbow extension and expansion that I discussed earlier. So here's our preliminary results of the bat flapping done using a kinetic sculpture made using laser cut components. So we're using laser cut components because it's stronger, so we can do some preliminary testing on it. We plan to use the soft and hard monolithically fabricated kinetic sculpture later to replace all of these rigid hinges. You can see that the wings folds and then expands as it folding during upstroke and expands during the downstroke. So you can see that's the kinetic sculpture over here. There's the flexible wing membrane that we plan to use flexible PCB later to and attach some of the sensors and electronics onto the wing to redistribute some of the weight from the main body to this wing. That will be part of the future work. That's all for this presentation. Thank you for listening, and do you have any questions?